let's get into it. So introduction, some goals we're going to discuss. So we were given the task of building a computational model to model a star orbiting a black hole in not an elliptical orbit, but also not like the black hole's not at the center, which makes things a little different. So some important physics, some goals of the labs to illustrate Newton's second law, as it's important to pretty much anything that moves, because most things don't go at a constant velocity, or if they do, they still, that law applies. Discuss universal gravitation, so that big G times mass 1 times mass 2 over r squared is going to be really important for this lab, because that is really the only force acting on anything for most of the lab. And then rotational motion will also play a role towards the end. Some physics ideas, sort of just hit this, but the net force, sum of all the forces, in this case, there's really only one. It's the universal gravitation and then rotational motion. Because the planet is orbiting, it is in rotational motion. Initial conditions for the setup in part one. So in part one, we have a black hole. We have a planet. Here are our initial conditions. The mass, it's not a planet, it's a star, sorry. The mass of the star is 2 times e to the 30. Gravitational constant is there. And then the delta t is just the time it takes for 1 day. That's 84,600 seconds. No, it's the number of seconds in a day. We get to the computational code. We first start by finding our initial and final positions. We find our delta v, our change in position as well. We then use that to find our change in momentum. And from there, we set that change in momentum equal to our net force. Then we find the parallel and perpendicular components of said momentum to find our parallel and perpendicular forces. And then the last part that is important is this bottom left corner where with the MBH, which is the mass of the black hole, which we set, we rearrange the force equation of F net equals big G times mass 1 times mass 2 all over our to find the mass of the black hole and to calculate it over and over again as we go through our orbit. On the right side is the code to show the arrows that are nice for visual but not super important, so I don't think I'm going to go over that. So my results for part one with the mass of the black hole we found after the program calculated it over and over, and I averaged it, I think just in Excel. So it came out to 1.41 times 10 to the 34th. Also are the final net forces, like at the final position where it stopped. So the total F net, the F perpendicular, the F parallel. Important to kind of note is how much larger the perpendicular force is than the parallel force, about 3 times as big, a little more than that, which is interesting to note. So the parallel and perpendicular components of force are a little different from the rate of change in momentum, and that the rate of change in momentum doesn't necessarily break things into forces on its own. However, we did set net force and change of momentum equal to each other, because momentum is mass times velocity, and the net force is equal to mass times acceleration. And if you have a rate of change of velocity is acceleration. So if you're doing the rate of change of momentum, then you have mass times acceleration, which is equal to that force. So they're not exactly the same, but they are very similar. For part two of the lab, we've got some more physics ideas. Constant orbit will come up in the sort of what if portion, and then escape velocity is important, which is not something we totally talk about or are going to calculate, but just it's important that so the rocket doesn't end up, inside the black hole. We want it to get close, but also be able to meet escape and not get sucked in. So here are initial conditions. We use the mass of the black hole found in part one. And then the computational code, we use the position and velocity update formulas to kind of move things along. And then the net force equation as used earlier as well. Here are the results. We've got the initial velocity of the ship that I kind of just trial and errored to see how close I could get it. This was sort of the best result I got to without doing a ton of iterations. I got negative 3.87 times 10 to the 7th in the x direction, 1.5 times 10 to the 6th in the y. And the closest distance this gets from the black hole is the number you see there, the 2.017 times 10 to the 8th, which is fairly close considering it's a, black hole. Discussion. If we want the rocket to orbit the black hole and to not have to fly straight away like it did in the model, our velocity is going to need our perpendicular component of force, which in this case is the gravitational force, is going to have to be equal to the F centripetal equation, the force centripetal equation of mv squared over r. So you set those two equal to each other, you do some math after you plug in some numbers, and you get v is equal to the number you see on your screen. So that's approximately how fast the rocket would need to be moving originally in order for it to not get sucked into the black hole and to just continuously orbit, assuming like a